Hello, welcome to Sunday Science Q&A. That was a particularly ebullient hello to wake you up to whatever kind of torpor or stupor you're in this final day of what we would consider to be autumnal summer. This is the week that in the most inhospitable planet it turns is packed with an alien civilization. Well, actually, I mean, in some ways I've exaggerated there. There's a hint of the possibility of life which may not entirely be fulfilled. That's not as good, though, as saying the alien invasion from Venus is imminent. So that's the angle we're going to go for. Today is we've got a lot of chemistry. This is one of the reasons that we thought this is one of the. It's a lovely thing when a moment of kind of a cosmological revelation is directly connected to chemistry. So we're going to be talking a lot about chemistry this week. I'll tell you a couple of things just in case you've not watched before. We've now done hundreds and hundreds of hours of programs. I mean, we did that before lockdown, but in particular since lockdown we've been producing hundreds of hours of stuff, and we try and make sure, like this, as much of it as possible is free to live stream and that you can kind of connect with us in as many ways as possible. So if you are able to support us via Patreon, that is fantastic. It really does make a difference, because for a lot of us who are involved in Cosmic Shambles, well, there's basically three of us who are predominantly involved in it, we don't have any work anymore. It's great. It really is. All of the live tours that I've been going on, they don't exist. So if you're able to support, that just means that we then now have a bit of financial backing to keep making as many things as possible. If you're not able to regularly support, don't forget there's a tip jar down at the bottom of the page or somewhere around the page that you're looking at. And if you can put something in that today, if you're able to, that's fantastic. If you are able to do neither of those things, please continue to enjoy watching everything that we're making. We try and make sure, as I said before, it's accessible to as many people as possible. Questions today, if you want to ask them in live chat, you can just go to the live chat, pop your question there. Our producer Trent will send them on to me, or you can tweet at Cosmic Shambles. So just at Cosmic Shambles, and we'll also find the questions there. I should also mention that because it's the big week of the phosphine week, that we also did a conversation, or I did a conversation with Chris Lintott earlier this week, and that is still up online. So if you want to see Chris Lintott explaining the day after the announcement of those, I think it is enough actually that what's happened to say that it is a revelation. He kind of ran through a lot of the different things that the possible changes in understanding, and indeed how the discovery of phosphine was made, and that was a great conversation. And there was a certain amount of serendipity in the how those discoveries were made. It was basically that there were in a drawer. It was a day where someone just looked in their drawer and thought, you know what, I haven't properly looked through these for ages. Let's have a little look. And while looking through old pieces of recordings, documentation, they went, oh, hang on a minute, I wonder if that's phosphine. And that links to the other person. This week we have one of our first science book shambles for a while going out, and it is with the Nobel Prize winning scientist Paul Nurse, who similarly, with serendipity, he was just mucking around in the lab, and he threw what he'd done that day away in the bin, and he thought, oh, well, there's nothing really to be found out there about cellular division or replication. And then after he finished his tea, he went, do you know what, I'm just going to cycle back to the lab and just check in that bin, because maybe there was something. And it turned out that really what he found in the bin was, a major part of the journey that led to him winning the Nobel Prize. So what I'm saying is, always do double check your bin before you throw things out. Also, I'll tell you that 9 lessons and our kind of Compendium of Reason shows, 9 lessons, which we normally do at King's Place, Compendium of Reason at Hammersmith Apollo. We're going to have some news about that very, very soon. I think it's probably going to be announced next week. Obviously, we're in strange times, and we're going to make sure that something happens, and we will tell you more about that later on. And also, we've got live Genetic Shambles at 8:30 p.m. on Wednesday, and that's going to be another COVID-19 Q&A. So if you have questions, and we'll do them quite broadly this time as well. I think we're going to do quite a long session on COVID-19, because as you know from things like the protests going on in Trafalgar Square yesterday, which were a very confused mix of people with a lot of different kind of agendas going on, and there are all manner, I've certainly found today on social media, different theories and different conspiracies, and so some of them have points, I think, which are relevant and interesting about the nature of the way the government is dealing with it. Some of them, I think, are tremendously problematic positions to take, because if you are worried that the government is going to use a pandemic crisis to bring in increasingly draconian measures, then ignoring all of the better health advice that you can get to try and curb the increase in a pandemic is not going to be helpful, because the more people who get coronavirus, if you think that this is going to lead to measures coming in which you see as being broadly fascistic, then also saying, and I'm not going to wear a mask and I'm not going to wash my hands, I'm going to hug and kiss as many people as possible, will ultimately be counterproductive for your aims. So there we are. Welcome to the show. That was a lengthy introduction. I hope I've covered a lot of ground there. In fact, that could be enough for today. Thanks for listening. Goodbye. Let's, as usual, I'm so pleased we have two people who, both of whom I've seen at the Royal Institution doing wonderful things. One of whom nearly killed us all with ether some time ago, who's Professor Andrea Sella, who we're going to be meeting in a moment, and the other is Professor Saiful Islam, who we're going to be also meeting in a moment. But first, our regular co-host, who is Helen Czerski. Helen, you telling me that your show and tell is particularly shambolic. There's a lot of entropy involved.
I'm regretting this already. So I try to find a show and tell which is relevant to the theme. And so I thought about pigments and colour. And so I've got ochre, and I'm going to tell you about it a bit before I show it to you, because once I start showing it to you, the mess will be everywhere. I will tell you that for the first time with the show and tell, my desk is covered with the only piece of plastic I could find in my flat. There is paper where I'm trying to cover everything up. And then I realised I was wearing a white top, which is a terrible idea.
See, this is great, though, isn't it? Because, as you know, this is, I can't remember if you were there. One of the great traditions with Andrea is that it is always, there's a terrible mess that, oh, I'm sorry, the mercury went everywhere. Oh, I wasn't expecting that to explode. When we did King's Place in December, everything was going to be wheeled on and everything was prepared. And just as that was about to happen, I can't remember whether it was liquid nitrogen or whatever. It was certainly something that was toxic should you fall on it, suddenly fell off the trolley. And so generally,
it was acid of some sort, because it melted someone's shoes.
That's right. Everyone went, why are my shoes so sticky? And why are they so much smaller than they used to be?
Anyway, so I'm trying to, I don't want to follow, I haven't got Andrea's experience at full expertise, so this isn't going to explode. So this, here we go. So this is ochre. And the reason I'm showing it actually is not, so the thing itself, so this, you'll have heard of ochre because it's one of the very famous early pigments. I can sort of draw on. This is a sort of reddish. It draws very easily. So it
my God, it's like looking at the caves of Lascaux. This is fantastic.
I'm going to put that. I'm going to stick this on the fridge now. So the point about this is not only is it a very strong pigment, but actually, and it's very messy and gets everywhere. So this is from Clearwell Caves in the UK, and it actually came in lots. So that if you wander around the caves, it's an iron-based material, or that's what's at the heart of its colour. The chemists can explain all this. But here are some other bits that were nearby, and you can see there's actually quite a range of colours. This one's got all this lovely texture on it. It's all got these little tubes, which is quite cool. But the point about it is that the chemists will, I'm sure, pick me up on the details, but fundamentally, it's all iron in here. But it's got lots of different colours because there's different particle sizes, there's different levels of water involved, there's slight different arrangements of the atoms in there, but the atoms inside all these three things are quite similar, and so these, because it's a sort, look at this already, it's everywhere. I'm going to start, I can't touch anything for the rest of the day now. It's like glitter, I know it's going to be everywhere. Andrea will know what it tastes like as well if I accidentally eat it. Anyway, the point of this is that a lot of the variety
probably paprika.
That is the voice of experience. I'll leave that experience to you. The point of all of this is that it was a very easy, if you lived in the right place and you could find a mine and pick it up, and you could be a much better artist than me at the caves of Lascaux. Look, it's falling everywhere now. You got a huge range of colours out of actually very similar chemistry, and so I just picked this as an example of the broad range of colours, because it only takes little changes in the structure to give different colours if you have the right transition metals, and all the chemists can tell you why that is. But yeah, so I just brought this along because it was I thought it was time it had an outing, and it is really cool stuff. It's just that every time you see a cave painting now, what you have to imagine is the artist walking out of the cave afterwards and their friends or family looking at them, just like, oh, like I once did I had a flower demonstration that used to blow up a lot, got flour all over me, and I used to walk out and people would go, oh, I genuinely thought you were a ghost. Yeah. So I want you to imagine the cave people, Paleolithic people walking out of the cave and their relatives going, oh, you've been drawing again, don't touch that.
That's great. That's lovely.
Yes, they probably weren't wearing white T-shirts.
See, Saiful, I've got to ask you. You mentioned tasting like paprika. Chemistry-wise, there is a line to be drawn somewhere, which seems to be quite blurry on checking the taste of something. Can I ask you, in terms of your greatest regret, in terms of just going, well, I just do wonder, what is this going to taste like? I think this element or this compound is reasonably safe to place in my mouth.
I think during my degree days, there was a kind of white ceramic solid. You thought it looked fairly benign, and I think it was a spinel or a mineral. And I did, just like you think, is it going to be like sort of an illegal drug? You kind of put it to your tongue, and it was disgusting. You had to spit it out straight away. I can't remember the exact compound, but that was my regrets. And I've never put anything to my mouth again, which I'm not sure about.
This is a very wide Q&A. It's also, a lot of it's about philosophy, ethics, good reason.
Good culinary chemistry, yeah.
See, I've always been told, that in the movies with the drug cops, they always go, yep, that's heroin. I've been told that actually that's not apparently an effective test. That if you're dealing with it on a taste.
I think that's probably where my role model came from, that kind of image. I thought that's the way to do it. That's the way to do it. And yes, do not do that. Do not try that at home. Yeah.
But that's amazing, because there's that thing. So I can't touch my face.
Yes.
No, do touch your face. It's going to make it funnier and funnier.
Oh, come on, just do that.
This is what we need. All that your face in public. Just put ochre on everyone's fingers before they go anywhere. It'll totally solve the problem. I've forgotten what I was going to say now. I have forgotten what I was going to say. Carry on. I'll remember.
Well, I think anyway, I'd like to get to do an episode if they ever bring back You Bet, in which various different blindfolded merely by taste, you will go across the entire periodic table. Well, until obviously you die. I've
remembered what it was. I've remembered my thing. It's not very interesting. But you know that thing where hair, as you growing it reflects the chemicals in you. So if you do take drugs, they sort of grow out in your hair a little bit, and stress hormones and things. Someone should test the chemist's hair, right, to see what they've been trying along the way. You're muted, Andrea.
Well, a couple of years ago, I made a documentary for Radio 4 and the World Service about mercury. And I was interviewing an expert on mercury and health. And at the end of the interview, I said to him, actually over the years, I've had mercury around. I've given lectures about mercury, and sometimes I worry a little bit about, whether I've actually acquired a fair amount of mercury given my eccentricities and so on. And he said to me, oh, look, you know what you have to do? Just do me a favor, cut a little piece of your hair and put it in an envelope and send it to me here in Denmark. And I said, okay, yeah, sure, I'll do that. And he said, oh, and by the way, why don't you get a colleague of yours to act as a control? And he said, find a colleague who eats a lot of fish. I thought, what? Okay, I thought about it for a moment. And then I thought, you know what? My colleague Beppe Battaglia, he's the guy. He's Sicilian, and I'm sure he eats a lot of tuna fish. So I went up to see him, and I got a little bit of his hair. We sent both lots off, and about 3 weeks later, the reply came back. The analysis came back. And it turned out that my mercury was kind of nowhere. So clearly my problems arise from something different other than mercury. On the other hand, Beppe's were 4 times mine, and in fact exceeded the National Institutes of Health warning level. And that's simply because of his fish eating. And so, absolutely, your diet will end up reflecting, or rather your hair will end up reflecting your diet. And so if you do, in fact, snort a lot of mercury recreationally, tuna for that matter, then we'll know.
Of course, there's far less, both of you and I, to be able to reflect our diet now, unfortunately. We become far more enigmatic with age in terms of our culinary treats. Saiful, what's your show and tell?
My show and tell. Well, first of all, I have to thank you, Robin and Helen and Trent behind the scenes for this kind invitation. It's a real pleasure to be on the first time. I have to say, talking to Andrea, I did a few butterflies before I came on. It felt like coming on for a PhD viva or an oral exam. I wasn't sure about the exam. Anyway, my show and tell is this. And I'll explain this model. There's 3 kind of very brief reasons. My research is all about crystalline solids. And probably the greatest example of a domestic crystalline solid is salt. You know, the stuff that you sprinkle on your chips, on your pasta. In my case, before a tequila shot. Actually, that's not true. It's usually before 2 or 3 tequila shots. So that is an atomic model. That's what it looks like on an atomic scale. That's salt. The second reason is to do with the research I do with these solids. I'm a chemist that doesn't wear a white lab coat. I do computer modeling. So I try and simulate these. So in fact, when I go to parties, that's when I get invited. That is, somehow, have you found that the invitations dry up when they find out you're a professor in chemistry or a scientist? Anyway, when I do get invited to parties and people ask me, Saiful, what do you do? I say, I model. But obviously I don't model down the catwalk. I use very powerful supercomputers. So the reason I use supercomputers to look at this is the third main reason for this show and tell is probably one of the biggest challenges of our lifetime is low carbon energy. And crystalline solids of this type are important in developing new materials for lithium batteries, but also for solar cells. And I use computer modeling to try and understand these crystalline materials at the atomic level. So that's my show and tell. I should say I prepared that earlier. Yes.
That's fantastic. Can I just ask you, just because I was interviewing Paul Nurse the other day in his life, and of course, one of the big problems is defining what life is. And there is a point where crystals come into play, where people go, well, hang on a minute, this behavior, this is shared. But so for you, what is the cutoff point between what we see in terms of crystals and what we would then define as being life?
Oh, God, that's a large, well, if you look at a lot of the, so if I go back a step, so in terms of crystal structures of biomolecules, I think someone did an analysis that it's one of the highest, if not the highest, awards of Nobel Prizes. One of our greatest scientists, Dorothy Hodgkin, Nobel Prize for vitamin B12 and others, crystal structures. So to answer your question, Robin, that's quite a difficult one to answer. So a lot of life, if you talk about, if you wanted to get the molecular structure of, say, DNA, the molecule of life, you can get the crystal structure. And Rosalind Franklin obviously did the famous photograph 51, get the X-ray diffraction pattern. And from that, you've got Watson and Crick working out the structure as a double helix. I think it's not a black and white. I don't think there's a continuum. So there is inorganic crystals that I look at. So these are inorganic, lifeless. There's no life here. But there are similar crystal structures that you would say are biological. And I'm sure Andrea has some views as well on that.
Well, I think my only view is that this is increasingly like a PhD viva. Your tormentor, the external examiner, right, who's just asked a completely impossible question.
But that's what I wanted to just check. It was still an impossible question.
Well, there isn't. Oh, go on then.
Sorry. I mean, I think my only comment would be that one of the things about life that we know is that life, in a sense, emerges from chemistry. And although we sometimes think of DNA as being the molecule of life, one of the things to remember is that all of the structures of biology that we see around us, whether it be membranes, whether it be the folding of proteins, whether it be the way in which the proteins actually sit in membranes and stuff moves through them, all of those are really the consequences of the simple rules of chemistry. And what you start to find is that the further away you go from equilibrium, and of course, when we're in school, we always think about equilibrium as being that kind of central place that everything comes to a halt and ends up there. If you're far away from equilibrium, then all sorts of very, very strange things start to happen. And it becomes possible now to start, for example, self-replicating, or to be able to shuttle things across membranes, those kinds of things to build in movement. And so I think, in a sense, the question of what is living and what is not turns out to be not something which has this binary distinction that we've always imagined, is that actually there's a kind of weird gray scale along the way. In fact, a multicolored scale, right? Where you go from things which are, a crystal of sodium chloride, which is, undeniably inanimate in one sense, to slowly the idea that crystalline materials might start to template certain things, certain other kinds of chemical processes. And as you go further along that continuum, eventually you get to this whole highly organized, self-replicating thing that we think of as being life. And really you're down, to thinking about COVID. Of course, are viruses actually alive or not, right? They are these beautifully organized chemical structures, which once they get injected into a cell are able to hijack the whole process, right? And then generate more copies of themselves. Are they alive or are they dead? Well, they're somewhere on that continuum. That would be my kind of take on that.
There's also another.
To get rid of the tormentor.
There's a step on though, which is I think that one of the ways that humans find out about things like viruses increasingly is trying to turn them into structures when they're not. So, for example, the diamond light source, it's a very advanced version of the X-ray crystallography that Dorothy Hodgkin used, but it only works if you can make say you've got a little virus like this, if you can make it line up in a regular structure. And actually, there's two hard bits to the process, and one of them is interpreting the patterns that come back, but the other one is just making this thing, which, as Andrea says, is really complicated, this little vesicle of something, just sit in a regular way so you can get the light to do what it needs to do. And so they can do that with the fact that you can image a virus. So they're getting so good at this kind of spectroscopy now that they can build 3D model, like they can actually effectively see all the atoms in a structure. And for a virus, that's really useful because it means you might be able to look at that and say, oh, well, if we tweak that one, we might be able to inactivate it and turn it into a vaccine instead of a virus. So actually, there is this additional thing, which is that humans are trying to force, in some cases, living, you can debate the viruses thing, but these complicated structures into a what is effectively a crystal, a regular structure, just so that we can see them, which is an interesting idea.
You're right. You're right. I'm turning this more and more into a virus. So now, Andrea, though, I'm going to hand it over to you, and you have a show and tell, an illustrated show and tell, I believe.
Yeah. So when I was asked for a show and tell, I was thinking, oh my God, I really can't sort of destroy something at home. In fact, the last time I destroyed a laptop. And so, it's best if what I do is I show you something. But something happened in the last sort of a week, 10 days, which seems kind of appropriate. And that's this discovery of phosphine on Venus. And lots of people have been asking me questions about phosphine. And it turns out that an astrochemist friend of mine asked me about a year and a half ago whether I could make him some phosphine and also some deuterated phosphine. So what I thought I'd do is actually take you through and show you how we would actually make it in the lab. And for me, it's a kind of rare opportunity to show you that actually doing chemistry can be unbelievably technical, right? But at the same time, when you do it, one of the wonderful things is that all of the physical laws that you learn in school and so to play. So, Trent, if you could just put up the first slide. I can't actually see the slides at the moment. So I'm not quite sure what's going to happen. But the first slide should, on the right-hand side, a little picture of phosphine. And phosphine is pH 3. It's like ammonia in a sense. And so it's phosphorus with 3 hydrogens attached to it. And at room temperature, it's a gas, okay? And that's kind of a problem because it means you've got to have a clever way to handle it. So one of the questions is, could you condense it? And it turns out its boiling temperature is about minus 70 degrees, and you can actually freeze it at minus 133. So actually make this stuff in the lab. And so here is the method that we actually use. What you do is you take a compound called zinc phosphide, which is a kind of blackish semiconductor you can make by taking zinc and phosphorus, but in fact we buy it. And then what you do is you react it with hydrochloric acid. And when you do that, the phosphine kind of bubbles out, and you get zinc chloride as well. But the phosphine, being a gas, bubbles out of it. Now, how do you actually handle that gas? So I think on the next slide, you'll see a fairly complicated piece of apparatus, okay? And you'll notice that I've used ochre to actually illustrate the diagram. So this was scrawled using ochre and a trackpad. And so it's I don't have a pointer, so I'm going to have to kind of take you through. Horizontally across there's what's called a dual manifold, and that's two kind of pipes of glass which have stopcocks in them. And those stopcocks are made of Teflon. They're called Young's taps. They were invented in Acton in West London by a brilliant glassblower. And a lot of us use those because they're just wonderful. They require no grease, very little maintenance, and so on. And what we're really doing is we're adapting methods that were first developed in the early 20th century by a man called Alfred Stuck to handle very air-sensitive gaseous materials. Now, he was working on hydrides of boron and silicon, and he developed all these methods. And the idea is really that what you're going to do is you're going to take the gas and then you're going to freeze it somewhere. And then once you've frozen it, you can kind of distill it, you can boil it again, and you can essentially move it from one flask to another. So one of the things you'll have are dewars, right? So vacuum flasks, thermos flasks. You're going to need a vacuum pump, which will actually allow you to have the vacuum so that the molecules will kind of move freely inside. You need a pressure gauge. That's absolutely critical. Those are your eyes so that you can actually see how much gas is where. And then you need to protect your pump with a liquid nitrogen trap. Okay, so on to the next slide. And this slide is called setting up the reaction. And you can see that down at the bottom, there's a flask and there's some black stuff at the bottom, which is the zinc phosphide. And those flasks are really important because it has a sidearm on the side. And that sidearm is really crucial. It has a stopcock. And so you can control whether it's under vacuum or under atmosphere through that tap. And then on top of it, we have hydrochloric acid, which we can drip in. And the whole thing is going to be under vacuum when we do the actual reaction. Let's go to the next slide. We now connect that flask onto our vacuum manifold. And we do that with yellow hoses. So that's the slide which says using a vacuum line. We put our zinc phosphide flask into some ice just so that the reaction will go gently, won't get too hot. On the other hand, on the other side, just to the right of it, there is a second flask of an evacuated, an empty ampoule, an empty sort of flask, which is sitting in liquid nitrogen. And in the liquid nitrogen, that means that we'll be able to condense the gas there. So now what we do is with everything under vacuum, and we've checked it with a gauge, we've made sure that there are no leaks and so on, we very, very gently dribble in the hydrochloric acid. And the hydrochloric acid causes everything to fizz. So adding the acid is the next slide, Trent. And you can see that it's foaming up above the thing. And so you kind of stir it and shake it and you watch it. You're watching the gauge, seeing what the pressure's like. And if we go to the next slide, you can now see the path that the gas is going to take. And so you can see that it's going to run along the hoses up to the manifold and then all the way back down into the flask on the right-hand side. And so you watch the gauge, you add a little bit of acid, you keep an eye. This takes about an hour in which you do the reaction, the gas is evolved, it travels across into the liquid nitrogen trap, and you keep everything under control. Okay, let's go to the next slide. So it gets a little bit messy. Some of the black stuff splashes around. But the crucial thing is the next slide, collecting the product. And what you see on the right-hand side is that in that flask has appeared a white solid stuck to the walls in the liquid nitrogen. And the key thing now is that you're going to have to separate that crude product because, of course, there will also be a bit of hydrochloric acid. There will also be some water vapor in there. There might be other things. And what you're now going to have to do is a very careful kind of separation. And you'll do this twice. So let's just slide, which is purifying the product. You now transfer the flask, which has the pH 3 in it, the solid, into a slightly warmer bath. So you put it into a bath, which is now at minus 78 degrees. You do that by taking dry ice and acetone. And now what happens is that the phosphine, it melts and then it vaporizes. And so it travels back into the manifold. Hydrochloric acid remain frozen. And so the phosphine travels through the thing. And what it does is it then condenses into a new flask. And so what you'll be doing is you'll do this a couple of times to make sure that you've really got it very nice and pure. And so by the end of this process, right, in fact, this slide is duplicated. We've transferred it, so you do that twice, you get the product. And so we have the next slide, and you can see we've got solid first. We let it warm up. That's liquid phosphine. You see it liquefy before your eyes. And then finally, you have an apparently empty flask, which is, of course, filled with a phosphine gas. So your phosphine gas is now ready to go. Working with a colleague called Steve Price, who may actually be out in the audience, and it's his experiments, right? These astrochemical experiments to understand the chemistry of phosphine under, in the presence of other molecular ions, and this stuff is really, really nice, well behaved, and so on, provided you don't make a mistake. What happens if you make a mistake and you let air in? Well, you get quite a nice, intense white glow in your flask. And what you get is orange goop on the walls. And that's my final slide if you make a mistake. So you've really got to be careful. And this stuff is technical, but my God, it's a lot of fun.
Thank you, Andrea. That was longer than the normal answer we have, but as 32 different people asked the question, if we divide it up, that was actually too brief. So that was great. That was really useful. We had so many people asking about this, and we will probably come back to this as well. But now let's get through some of the questions, because we've only got about 20 minutes left. Let's get through. But as I said, a lot of people asked about phosphine, so that was really great to go through all that. So let's start off with we got a battery-based question. So Saiful, if I can ask, I'm going to start with you on this, because I know that's one of your areas. This is from Philip. Philip would like to know, I've always wondered and always argued with relatives, but never truly investigated the difference between brand batteries and whether they actually last longer than budget batteries, or are they like paracetamol and it's all the same?
I missed that last bit there, Robin. You got cut off.
Oh, right. So basically, it's the difference between the big name brand batteries and the kind of budget supermarket batteries. How different are they really, or is it very much like supermarket paracetamol and all the other forms of paracetamol?
Being a humble materials chemist, I haven't done a extensive survey of the different types of batteries. In terms of cost, you would suspect that just the amount of material in the standard brand, the supermarket batteries probably might have less of the energy storage materials in there compared to the big brand, the bunny type brand. So that's my suspicion. I haven't done or read the relevant literature whether there is a significant difference. The composition of the materials would be very, very similar. I think in terms of cost, I suspect it's just the amount of the materials are in there and the way they're processed to bring if the supermarket ones are of a lower cost, then that's probably reason. But that person will probably still carry on arguing with their parents or grandparents, because I can't say a definitive answer on that one.
What is the most costly part then of a battery? What is the thing that would that with the ones that keep those bunnies drumming and drumming and drumming,
it's often the material. So for the lithium ion batteries of electric vehicles, it's the materials themselves. So for example, cobalt in the lithium ion battery is costly and toxic, so they're trying to bring down the amount of cobalt in those lithium ion batteries. It's the materials cost often. The actual manufacturing, putting the batteries together, has come down. There are some standard processes. some materials are just more costly than others. So one of the areas that we're looking on, this is through a big funding agency called the Faraday Institution, is trying to bring the energy density up and the cost down and the safety up. So it is materials costs.
Brilliant. So that's means the argument can continue. So it gives them a reason to continue meeting, which I think is important. No, Helen, there's no time for it. I'm going to go straight on with another question for you, Helen, because we're going to get through all of them again today. Which is, when does, and this is a big question, when does chemistry become physics and vice versa?
Oh, how to start a fight.
Yeah, exactly.
So there are some people who are of the view that all the interesting bits of chemistry are either physics or biology, and that is an opinion that is out there. So there obviously aren't clear lines, because when you come down to the nuts and bolts of chemistry, a lot of it was things that physicists found out. Just because if you're dealing with the nature of the atom and how electron fields work and all of that, you use that for chemistry. So I'm not going to start a fight here. I would say that you could argue that there's a mechanism thing, that physics deals with or let's do it the other way around. That chemistry deals with the electron, how electrons clouds interact with molecules, and all of that, anything that's caused by that becomes more chemistry. So that's how atoms basically sit next to each other and behave when they're near each other and all that kind of stuff. And the physics is perhaps a bit more about why that happens, but then physics includes everything else as well. So I haven't got a really good answer, but I am very aware that if you wanted to start a fight in a university common room, that would probably be a really good place to start.
See, I do think there's something when we start actually placing it on a kind of an imagined timeline, to say when the universe starts, it is physics, and then at a point in the universe, chemistry, and then biology. And when you actually see that and that's not in any way to lessen any one of those things, I find that very fascinating, where, physicists that I talk to who talk about ideas which I find tremendously intricate, they will always say that ultimately physics is very simple. And then you get to chemistry, and chemistry becomes more complex. And then biology, of course, we might have, some biologists will say biology does have a unified theory. But despite that, every time you get which would be Darwin, theory of natural selection, they would consider that to be their unified theory. Then every time you get an answer in biology, though, you go, oh man, that's a lot more questions. That's made it a lot more confusing. And now that to me is an interesting way of just thinking of it as the evolution. Physics.
But all of these things are about interacting. And so it's like a Venn diagram where they overlap in different places. Yeah. Ultimately, the interesting thing is the human body and the planet and the universe. All of that. You look at those big systems, you say, what's inside the system? And it's just that to look at different bits inside the system that are certain size scales or act over certain time scales, you need a certain type of expertise, but they all merge together. Like, the physics of complex, and I'm talking about the Earth as a complex system, all of it, that does involve physics, and it does involve chemistry, and it does involve biology, and after a while, it's like even with the ocean, no one really trains as an oceanographer. They all start off as we all start off as mathematicians or physicists or something else. So it's just like the scale and the type of your approach that dictates your discipline. The only reason people think there has to be a separation is that someone at school thought that was a good idea. I mean, there is no reason. If I was doing it, I would have, the human body and the planet as the two fundamental subjects, and dig around inside those. So I don't know. What's interesting is you identified there's this legacy from the past that the order of things kind of goes like that, although they all started off as alchemists or biologists, I suppose, if you start further back, people looking at animals. But it's that, do we have to keep that system? Do we still need chemistry, physics, biology and maths? Or is there a better way of splitting up the perspective that you start teaching from?
See, I don't see it as splitting up. I think it joins it together. I think that when I try and imagine in my head that the universe has this point where it is physics and the equation of physics, and then it gets to a point of complexity which brings in chemistry, and then it gets to a point of complexity somewhere or other. Currently it only seems to be here, but obviously that is only all we know. It becomes biology. I think that joins them all together rather than turns them into, as you're saying, the school curriculum thing. Andrea?
Physics, chemistry, biology, and so on. Those are all things which, just as where we talk about physical chemistry, organic chemistry, inorganic chemistry, these are divisions which are really designed because you can't teach all of it in one go. you've got to kind of fragment it somehow to be able to kind of package it up. And so one of the really interesting things is that because we end up with this kind of chemist mindset or physicist mindset or whatever, it's always at the interfaces between them that really interesting things happen. And I think no one should underestimate how important mathematical biology and biological physics, are at the moment. And, because we come out of a school thing, we don't imagine that maths really impinges on biology. Oh my God. And similarly in chemistry, right? Sort of similar things kind of apply.
I think that's an interesting bit. Again, it's something I suppose we need to get more into the public, which is when we've done some of the shows about COVID-19 and people have said, why have you got mathematical modelers on? What's maths got to do with anything that's, and all of those things seem to be gut reactions. I think, again, partly based on a curriculum which doesn't necessarily connect in the way that it should. I'm going to ask you this question, Andrea, because I think it's meant for you. I went to last year's 9 Lessons show, as I've done every year, and each time before Andrea is on, Robin tells some story about Andrea backstage, and I never know if it's just part of a joke or real. So last year, did he really knock over a massive jar of sulfuric acid before going on stage? And I'm going to add to that, can you tell us, as long as it remains happy and no one dies, your worst clumsy error dealing with noxious?
Oh, wow. Okay. All right. So I mean, what happened last year was that I was going to do a demonstration involving hydrogen, and I was going to make the hydrogen using a very ancient sort of 19th century piece of apparatus called the Kipps apparatus that I knew I owned, but it had disappeared. And in fact, I found a circle in the dust on a filing cabinet where it had been, and someone had borrowed it. So I got in touch with a friend who makes apparatus, and I said, "Hey, have you got one? Can I buy one?" And he said, "I'll send it to you." So he couriered something the day before the 9 Lessons, and so I got the thing, I set it all up, and so on. And at the bottom there is a stopper which fits into it, and I put a clip on to hold it. What I hadn't spotted was the fact that the clip was of the stopper and the joint were actually of a different size from the standard ones. And so the clip didn't fit properly. So backstage, I got the whole thing set up and I started letting in some of the sulfuric acid. And suddenly, just before we were due to go on stage, sure enough, we heard a blink, glug, 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 glug. And the sulfuric acid started pouring all over the floor and onto my shoes. Yes, indeed, it did make a few holes in my shoes. It wasn't that concentrated, but my shoes were quite flimsy. So that was, on the one hand, highly embarrassing. But on the other hand, it did give a certain manic energy to the whole enterprise, which I think quite a lot of people in the audience quite appreciated that evening.
Well, you'll see that, Andrea's face has a kind of Stan Laurel shape to it. Mine has a reasonable Oliver Hardy shape. So generally at the end of every experiment, it's just me. So so what is the worst one that you've had? I'm trying to think that in terms of our experience. Generally, it's been, there was that bin that we blew up at the Birmingham NEC, but no one knew about that. So that was fine.
Steve pretty tells you being genuinely worried while melting a trumpet.
Yes, we did film the burning and melting of a trumpet, which we did in a fume hood, and the fume hood, the trumpet did catch fire rather spectacularly after a while, and there was a brief moment of real fear before we got the fire extinguisher onto it and put it out. So yes, there was that. There have been a few others, but should save those for a day when we can sort of relax in the pub and kind of exchange.
A day where you're not at the house. A day where you're not at the house and you don't have those terribly, those staunch draconian domestic rules that don't allow you to set fire to the living room. This question from James M. This is another battery-based question, which I hope is okay. This is, could lithium-ion batteries be used in large farms to power cities and recharge them via solar? And what would the environmental impact be of actually manufacturing that amount of batteries?
So, good question, or two questions. First one is a yes. In fact, energy storage for renewables. So when the wind isn't blowing and the sun isn't shining for solar, is critical. At the moment, it's largely dominated by pumped hydro, but quite a few companies, and not surprisingly, Musk and others are looking into large-scale energy storage using lithium-ion batteries, but also for your viewer, sodium-ion batteries. Sodium is more abundant than lithium, so in essence, it's much lower cost than lithium. It's got a lower energy density, i.e., you can store less energy in a sodium-ion battery, but for renewables on a big farm, size isn't as critical. So you could use sodium-ion batteries instead of lithium-ion. But in both cases, yes, they are being developed. On the second point, there's big projects here and Europe and in the US on recycling. The problem with lithium-ion batteries is that because they're multi-component, trying to extract the different components, the important components, can be sometimes more costly than just, unfortunately, just getting rid of them. So there are big research efforts to try and optimize recycling. I discovered recently that we recycle 98% of lead acid batteries, quite a high percentage of lead acid. We need to get that kind of level eventually when electric cars become big, more volume, to recycle it. But for local grid storage, for that local farm of wind farm or solar farms, recycling will be less critical because you want those energy storage farms to last longer, maybe 10, 20 years. So the demands on there is lifetime rather than energy storage.
I have been actually to car recycling plants where they cold process, so no smelting anything, but it works. So it people are coming along where they are doing that kind of thing, and they're doing it with car batteries now. But also you can use a car battery obviously several times for different things before you have to recycle it.
Yeah.
And the other thing is that recycling of lithium batteries, although it's not common, you tell you that you can't do it, in the supermarket or whatever. But in practice, recycling of lithium batteries has really come on a hell of a lot in the last 5 years. And so it's becoming big business. And in a way, the batteries are partly to kind of store the energy, but they play an incredibly important role with renewables in stabilizing the grid. And so there's been this remarkable project, which you will remember. Elon Musk made this bet in Australia that he could provide a huge storage battery within 100 days, or they would get their money back. And Musk did deliver. And it has really transformed things, because one of the things is that it is far faster and more responsive than any technology in being able to make up for sudden surges in demand or sudden drops in production. And so it's really been a tremendous success, and that stuff is being rolled out elsewhere, including the UK.
Yeah.
But also, batteries aren't the only solution to that problem. Hydrogen is, there are big projects now on the northeast of England where stuff's coming in straight from wind farms. Whenever there's a spike where they would normally turn it off basically because the grid can't cope, it goes into hydrogen storage, and that is a very good long-term storage that's suitable for bigger vehicles. It's a very flexible thing, and so I think all of these things, they are happening, and batteries, although they're really important, they aren't the only solution.
I view the kind of energy supply as a pie chart. There's as currently different parts of the different wedges of that pie or cake will be different types of technology, and hydrogen, lithium, we've got biomass, we've got nuclear will be part of that as well. So there'll be different aspects depending on, I suppose, different types of requirements required. But Andrea is right that smart grids in the future will use the batteries or hydrogen as load leveling. So it makes it much more efficient, the supply of energy in the UK and worldwide.
And I think
right, we're going to move on. We're going to move on now, just because we've got 10 questions left and we've got 9 minutes to go. So this is from Kaylee, who's age 10, who would like to know: could we find a new element on another planet that would fit in the middle of the periodic table, or would it have to go at the bottom? So this is a very interesting thing about Mendeleev and the periodic table kind of came together. So Andrea, what do you what would we know about if we found something else, a new element? What would we?
Well, I think that the only elements that remain to be discovered are the ones down. And the reason is because of the structure of the nucleus. And the nucleus contains particles called protons. And what we know is that as you go from hydrogen through to uranium, hydrogen has 1 proton, and helium has 2, and lithium has 3, and beryllium has 4, and there are no gaps. And what that means is that there is not going to be any element between hydrogen and oganesson, which is the last one that was discovered, that is being discovered, that is confirmed, that is agreed.
Yeah.
But beyond that, wow, there's still options. And what I suggest you do is very soon you should get your parents to get you a book called Itch. And Itch is the story of a boy who discovers element number 126. It's quite good. It's quite fun. And I understand there's going to be an opera based on it too.
That's great. That's great. That's by Simon Mayo, and that is who basically started writing a book about science because one day he found out he didn't know what the 4 forces of the universe was. I think his son, who was about 9 or 10, said, "Dad, what are they?" And he thought, "I don't even know what they are, so I need to learn." And I might then use a book. Yeah, it's a great way of turning that into something, a journey of discovery. This from Karen Lawrence has lots of different questions. I'm just going to throw this one at you. She would like to know, why is chemistry so fiendishly anomalous? Now, who would like to pick up on that? Andrea, go on then. You go first. Everyone else can join in. Go on.
Well, I suppose I want to know what she meant by anomalous then.
Well, that's exactly what I want to know as well. So I was wondering if you have had more people saying to you that chemistry appears to be an anomalous discipline. Andrea?
I mean, I think anomalous is a very slippery word. But one of the things about chemistry is that it has a very strange paradox to it. And that is that on the one hand, it seems to be about very familiar things. But on the other hand, it's unbelievably abstract. And the rules underpinning it seem very, very alien. And it takes, a lot of work to start to get to kind of really embed that and feel them deep down. And I think that's what she means by anomaly, is that, you look at the periodic table and you have no idea why things are structured that way. And actually getting to that is complicated in a way that perhaps some of the laws of motion or those sorts of things maybe are less so.
But you can't see the mechanism, right? When you have a dog, you go, that's a dog. That's definitely biology. It's got some lungs and it's got feet and it's got ears. And those are definite biology. And I can see how they work, at least on the surface. And when it's physics, you go, okay, sunlight, it's passing through a window. I can kind of see what's going on. But with chemistry, the mechanism is absolutely invisible. And that's why I think people
utterly alien and mysterious. Yeah. I mean, what is the mechanism underpinning a dog?
But the point is, you can see some of the mechanism. You can see what it is.
Can I say that chemistry? I don't think chemistry is anomalous. Then yes, I'm gonna say I disagree with that proposal. That it isn't anomalous. That it's got a lot of. You brought up the periodic table. Well, I like the periodic table. It is structured. It's a bit of structure there. I've just shown you a lovely crystalline model. That's not anomalous. That's nice and regular. You get salt anywhere in the world, and it would look like this.
Right. Okay. Well, I hope that's brought some satisfaction to you, Karen. This is a question. Someone says that you were tweeting, Saiful, about a lemon battery and the world record the other day. Yes. And LW really. The question is, a what now? So, if you could explain the lemon battery.
So, in a minute, I'll explain. So, during my Royal Institution Christmas lectures, the last of the 3 was on energy storage, and I showed the audience how a battery works. And a school experiment that Andrea knows is using a lemon. I stuck in a copper nail and a magnesium strip, connected it up, and we generated 1.4 volts. I told the Royal Institution, that's fairly dull. Can we go large? Can we go very large? And so I got my research group to buy 1008 lemons. They cut them in half to get 2016 lemon slices. So that was true cutting edge technology. Boom, boom. And they put them onto some IKEA shelves. We got all the leads. We got the Guinness World Rep in, and we generated nearly 1,300 volts. So it's a world record in terms of the highest voltage from a lemon battery. The certificate is behind me somewhere over there. I'm in the Guinness Book of World Records for the highest voltage for a lemon battery. And we recycle those lemons afterwards by lots of gin and tonics.
Right. So, yeah, on Pancake Day, generally have syrup instead of the lemons. Because
yes,
when Alessandro Volta first discovered that you could make lemon batteries, he didn't use lemons, but anyway, he dipped copper and another metal into a glass. The way in which he tested the voltage was actually by taking the two wires and first touching them both to his tongue. He then followed that up, and because he could taste something, and he stuck one wire onto his tongue and the other one in his ear. And then he heard an amazing noise as well as having his tongue twitch. Then he connected his tongue and his eyeball, and he saw a flash. So my question to you is, did you do the first one and connect up to the 13 kilovolts?
Definitely not. Definitely not. No. Very much.
Well, as we've now talked about the discovery of ECT therapy, the next question is a lithium-involved question, which is Susie would like to know how excited should we be about discoveries of lithium in Cornwall? Helen?
Oh, there's been lithium in Cornwall for a long time. So the thing about mines that people tend to forget is Cornwall has loads of tin and all kinds of interesting things. Yeah. And the thing about mines isn't normally discovering them. It's whether the price of the thing that you're getting out of the ground is worth the effort of getting it out of the ground in that place. And there are plenty of deposits that we're not short for most elements of knowing where they are. It's just a case of whether the price of it is enough to get it out of the ground. And so there's been a lot of talk of artisan mines, which is a wonderful phrase. And, it's a local industry for Cornwall. And if the price of some of these things hits the right point, it either becomes inaccessible elsewhere and the price goes up, or they find new methods of mining it, so the price in Cornwall goes down, then the mines may well open up again. So it's not really discovery. The geology of Cornwall has been very well known for a very long time. It's just maybe they found a bit that's maybe a bit richer, so a bit richer in the deposits, so that would bring the price down. But it's all about whether it's worth getting it out of the ground. And actually at Clearwell Caves, the Ochre that I just they have had a mine there specifically for artists for something like 200 years. And when I visited and got those samples, they actually said they were close to the end of the line because people weren't prepared to pay for it anymore after more than 100 years. And the ochre is still there. It's just that, health and safety regulations come in and make it more expensive. And so it makes it harder for small scale production facilities to work. But, maybe in Cornwall, there'll be lithium mines again.
We're nearly out of time, so I'll just remind everyone if you are able to support us via Patreon, it really does make a huge difference, especially at the moment. We're trying to make as much stuff as possible, have as many people with all manner of different levels of expertise and passions on these shows, and we have had well over 1 million people watching the stuff that we do, and we have produced hundreds of hours of stuff during lockdown, and we do kind of need, though we try and make all of it free, we aren't able to make everything free, and we're really trying as hard as possible to keep this going. So if you're able to support us via Patreon, or at the least just pop something in the tip jar, that's fantastic. If you're not, I hope you keep enjoying what we're doing. I have to ask this from Johnny Dobbo, because I have no idea what this means. This is one of the lovely things. So many questions, I have no idea what they mean. Johnny would like to know retrosynthesis. Why? So retrosynthesis, who's going to go for that?
That has to be Andrea. Come on.
Right.
Synthesis. Why? So one of the things is that we've, we keep finding really interesting, complicated biological molecules, mostly molecules from nature. So what you do is you find some tree in the forest, right, and you go and squeeze it because somebody tells you that it will cure a certain disease. And this is often the process by which drugs are kind of brought eventually to market, is that you have some natural product out there Now, the thing about these natural products is that they're often very, very complex. And so there's a real challenge for chemists to try and build that from scratch rather than following the biological pathway. So how could you do that? How could you develop a route which starts from almost the elements, or at least common things that you can buy from a chemical supplier, and then make this really weird molecule, I don't know, bryostatin or ampicillin, or I don't know what, something like that. Retrosynthesis is a kind of mental game that organic chemists play, in which what they do is they essentially deconstruct a molecule. They pull it apart, essentially saying, if I take it apart here, I can put that back together again using this chemical reaction, this step. So, okay, we'll take that apart there. Now let's remove this fragment. And so what you do is you deconstruct the molecule into eventually simple building blocks that you can buy off the shelf. And then what you do, now you're ready to attempt the complete synthesis of this molecule. And now you attempt to reassemble the whole thing. And through this kind of mind game, which doesn't really have a commercial application, what's come is an extraordinary knowledge of the rules that govern organic chemistry, the way in which you can assemble molecules. So it's fascinating, it's really hard, and it's one of the things that an chemistry undergraduate will have to go through in order to get through advanced organic chemistry.
Thank you so much. Thank you all very much. I'm sorry for the questions that we didn't have time for. Some of them we will come back to, because some of them will remain relevant in various other shows. And I will just mention again, we have the interview with Paul Nurse. That's going to be up next week, talking about his book, What is Life? And we talked about a lot of different things as well. And it was, the stuff that we know about yeast, and the fact that basically 1.5 billion years of that's how long certain ideas in life, we can see the continuation of what goes on within us and what goes on within yeast. And that is a really incredible and beautiful story of connectivity. We're also doing another COVID-19 special on Wednesday. We're going to try and do some more stuff on COVID-19. We're going to try and do some more brief things which will just be explanations of why scientists and medical people believe that masks do have some use, why they believe this is not something that was manufactured in a laboratory, why they believe this really does exist, that COVID-19 exists. We're just going to deal with some of those kind of things as well. And we're going to predominantly deal with genetics on Wednesday, but we do want to have answers that are useful for you sometimes when you're involved in arguments online, etc., of just looking at the evidence, and also talking to some of the doctors and nurses and people who are on the front line and dealing with these things as well, for them to explain why sometimes something which can seem very disconnected to those who have not in any way been affected by it, why some of these things, why I know some people feel that there's overreactions, etc. So I think that's why it's very important as well to talk to the doctors and nurses and those people dealing with that now. So we're going to try and do that over the next couple of weeks. So as I said, COVID-19, we're going to do that on Wednesday. I'm not sure what next week's theme is going to be on the Sunday Science Q&A, but we'll be back at 3 p.m. with that. There's more book Shambles coming up as well next week. Thanks very much for watching. Thank you to our producer, Trent Burton, who is in agony with his lower back, because he's been in the same chair now for 6 months, just producing all of these shows, and eventually it has led to all manner of lumbar complications. Have a lovely rest of the weekend, and we hope to see you during the week. Bye-bye.
Bye now.
All right.